Today you are in MNCF. It's a facility under the aegis of Center for Nanoscience and Engineering, Indian Institute of Science, Bangalore. My name is Dr. Abhishek Chaturvedi, and today I am going to explain you the basics and how the basic operation works for scanning electron microscope. In the first segment, we will see the sample preparation. In the second segment, we will see the tool operation, and in between we will discuss the basics of scanning electron microscopy, and then further we will, towards the end of our slot, we will see different applications of SEM and what kind of images we can produce for SEM. So as you must be aware that SEM is a very important tool in terms of your morphological imaging or for chemical composition or for any other application where you wanted to know about the morphology or composition or the shape or the size of the particle which is less than 300 nanometer, right? So up to 300 nanometer your optical microscope may work. Below that length scale you need scanning electron microscope. So before explaining any further SEM, I am going to explain you the sample preparation. So as you can see here, I have different kind of holders. These are stub holders and these are different kind of stubs. So you can see the interesting part here is that we have a flat surface where we can mount our sample like this. I have prepared few samples for you. So you can see I have pasted these films over the carbon tape. So we have a double-sided carbon tape like this. We have cut a small piece and over which we have pasted your sample. Now, if you have a powder sample or any other sample, you can make this kind of sample. The advantage with this kind of stub is, what you can do is, if you want the top surface morphology, you can mount the sample like this. You can mount the sample like this. If you want the thin film, you can mount the sample like this. So you will be able to see the outside layer thickness you can measure of your thin film. Now, many a times you have a feature which you need to be inclined at 45 degree or something. In that case, you can mount your sample like this at 45 degree and you can observe the feature. So in the one stub, you can mount the sample in 3 types according to your need of information. So as you can see here, I have a multi-stub holder as well. What I can do is, I can paste one sample holder, second sample holder, and then this one also we can add. What it do for our advantage is, as you know, SEM is a vacuum instrument. It uses vacuum to achieve the electron beam. So once you keep all the samples inside, you don't have to break the vacuum again and again in order to insert the sample. So today what we are going to do, as you have already seen, we have different kind of sample. We have some films here. We have some films here. We have powder samples. We have thin films. And these are different kind of holders which we use. Okay. Today for our demonstration purpose, I am going to use gold on carbon standard sample. This is your gold on carbon standard sample. What we are going to do, we are going to image this sample up to 2 lakh magnification. Generally, for most of the 90% of the users, they use secondary electron imaging up to 50,000 or 1 lakh. Here we are going to image this sample up to 2 lakh, and also we are trying to find out different kind of signals. So I will explain to you in a minute during the pumping operation what kind of signals and detector we utilize for different operation. So today in a nutshell, what we are going to do, we will take gold on carbon standard sample and we are going to see first the secondary electron images using 2 detectors. First we have Eberhardt only detector and second we have in lens or through the lens detector. After seeing the secondary electron images, we will go towards the backscattered electron images. I will explain to you what is backscattered and why it is important to us, and finally we will also trying to find out the chemical composition of our material. With this I am going to start my preparation for gold on carbon sample. So this is my gold on carbon sample. I have used the single stub holder and I have kept the sample here. Now what we are going to do, we are going to keep the sample inside the SEM. So I will show you in a minute what are the different operations of SEM and about the SEM console. So as you can see, I have already prepared the sample here, gold on carbon standard sample, which we are going to image. Now I am going to break the vacuum. Here you can see that there are two vacuum levels. One is system vacuum. You can see the reading 1.5 into 10 to the power minus 5 millibar, and then gun vacuum 1.83 into 10 to the power minus 9 millibar. Please note that we are only going to break the system vacuum. This is my system vacuum or chamber vacuum to be precise. Now I am going to press the vent button here. Now I am clicking. It will ask me whether you want to vent to avoid accidental venting. I will press yes, and then you will see that now system vacuum has become grey. Now we will wait for the door to open. So now I am going to open the door. Okay, so now we have opened the SEM chamber door. Now as you can see here, I have a sample ready which I have already prepared, gold on carbon standard sample. You can see that there is one stopper line here, right, and there is a circular thing. So what you have to do, you can see that there is a groove here, right, and then you just have to push this from other side of the line and make sure that stopper line has been hit. So now sample is set. Now this stage is an interesting thing. It has 5 degrees of rotation, like one is X. You can see the stage is rotating, X, Y, tilt or Z. So these are the operations of the stage. There are 5 operations. I will show you in a minute in the camera mode also. So now I am going to pump my system. So as you can see, I am slowly pushing the door back. So here I have pump button. Earlier you saw that I have vented the system in order to make the system vacuum. Now I am going to pump it back. So now you can see the moment I have put the vacuum thing, the one clock is being displayed here, right? Once it will become like green, our system vacuum is ready, and you will see that value in system vacuum will be somewhere near about 5 into 10 to the power minus 5 millibar. That is the threshold value. Below that you will see the green tick here. So as discussed earlier, now we are waiting for vacuum to attain, right? Meanwhile, I am going to explain to you the basic theory about the scanning electron microscopy. This is a typical principal schematic diagram of a scanning electron microscope. We have an electron gun. Electron gun is the place where we have a filament which will produce the beam of electrons for us. Then we have a vacuum chamber on the outside which consists of electron gun. Then I have different lens systems, condenser lens, and then we have objective lens. This beam of electron is coming, and finally we have the sample chamber where we have different kind of detectors. As you can see here, I have X-ray detector, I have backscatter detector, I have secondary electron detector. So this consists of the basic structure of scanning electron microscope. Okay, so now quickly we are going to go through this presentation which will give you the brief idea about the SEM. Here onwards I will refer scanning electron microscope as SEM, right? So first the principle of SEM, then basics of imaging, what are different parameters or words you will encounter every time, then different types of lens aberration, parts of gun, different types of signals, and then different parameters which you are going to use while handling the SEM. This is very important, as you should, if you are aware of these parameters, you can play around them in order to get the optimum image of your material. Now this is a very important diagram. I will just take a couple of seconds in order to explain you that. Here you can see we have different techniques. We have optical microscope, we have profilometer, SEM, TM, AFM, but different length scale. You can see SEM covers from optical microscope and reaches up to TM. So it means that it's a kind of a universal instrument from mm level to nanometer level. you can work with SEM. Here is a brief comparison I have done for the comfort of the viewers, that I have an optical microscope, SEM and TEM. So you can see in terms of applied voltage, we simply have a 10 volt bulb in optical microscope, halogen lamp. In SEM, we are applying 1 to 30 kilovolt of accelerating voltage. In TM, we are having 60 to 300 kilovolt of accelerating voltage. Now magnification we have up to 1500x in this particular model. We can go up to 10 lakh x. Today we are going to see one image at 10 lakh x on iron oxide sample, and in TM we can go up to 50 lakh x. Resolution, this is a very important parameter viewers. We should always take consideration of resolution. In optical microscope we have 300 nanometer resolution. In SEM we can go in best conditions up to 0.5 nanometer. Presently the resolution of our tool is somewhere around 1.2 to 1.5 nanometer, and finally with TM 0.05 nanometer. So you can see just the order of magnitude is improving in TM, but it will help us to capture very important information. Now again the principle of SEM, you can see once the incident beam fall over the sample, we have secondary electrons, backscattered electrons, X-rays and other electrons. Now basics of imaging. So viewers, magnification. Magnification is nothing but the relation between digital world to your physical world. So already you can see area under the CRT and area on the sample. CRT you can consider as this screen, right? Now magnification, often you have heard of the term that I have taken images at 1000x. At 1000x the meaning is somewhere around 100 micrometer by 100 micrometer area you are scanning. Similarly, if you are taking image at 1 lakh x, you are talking about 1 micrometer by 1 micrometer area. So it is very important to note down these things, because many a times we take it for granted, but these are very important things for our purpose. Now demagnification. Please understand, demagnification is not the inverse of magnification, but it is just the process of chipping out the beam which is coming out of your filament, right? Gun is producing beam, electron beam. The process of chipping it down with the help of apertures, with the help of condenser lens, with the help of objective lens, the process is known as demagnification. Now the resolution, as you can see, the resolution is the smallest distance that can be distinguished between the two particles. So just to give you the feel of the numbers, these are some basic formulas using arithmetic, right, and trigonometry. See, given at 100 kV, which is actually not possible, we have taken this number into consideration just for the ease of calculation. At 100 kilovolt of accelerating voltage, the resolution of the tool will become 0.24 nanometer. So as we have already discussed in terms of TM, we can easily resolve these kind of particles, right? Now depth of field and depth of focus. Yes, one of the key features and advantages SEM offers us is the depth of field. Now the depth of field is very interesting. If you have a sample which has a very rough surface, or there are undulation in your sample. Now in optical microscope, even at a smaller magnification, you will see that one part of the area is blur and other part is focused. Whereas in SEM, even if the sample has undulation, the same sample, there is a good chance that you will be able to resolve the sample area equivalently. Now just again to give you the feel of the numbers, this is again a formula which we have derived using some basic trigonometry, right? Optical microscope at 1000x magnification, the depth of field is 1 micron. That means if there are two particles adjacent to each other and if the difference is more than 1 micron, you won't be able to focus simultaneously. Whereas at the same 1000x magnification, depth of field for SEM will become 40 micrometer. So it's a huge difference when you are talking about some microstructure or fracture surface, or those who are working in materials with the system or MEMS devices, where you have a situation where you have one end is a valley and other end is a peak. So again you have depth of focus, it is nothing but in case 1 we are changing the object plane, in the other case we are changing the image plane. Now I have only one slide, and which is very important in terms of signals. So this is the slide which I am going to explain to you in a minute. I want you to focus on this axis. You can read thickness D is equal to nanometer, and then there are different kind of signals. Now read out. The first signal which comes out is from here, top surface, which is Auger electrons. Now Auger electrons is a signal which is most of the time is absorbed by the beam itself, which is the incident beam. It is absorbed by the beam itself. We have a separate technique known as Auger electron spectroscopy in order to deal with Auger signals. The second important signal which comes out is secondary electron. Secondary electron is the most common class of signal which provides you topographical information. So most of the users who are going to use the SEM or who are seeing this video, 90 to 95% of the users typically use secondary electron signal in order to find the topography and morphology of their material. The second important class of the signal which comes out is your backscattered electron. So as the name suggests, these electrons are backscattered. So first one is the using elastic scattering, and another one is using inelastic scattering. The backscattered electron provides us the atomic number contrast. With the atomic number contrast, if you have a situation today like when we have like gold and carbon sample, right? The gold particles are embedded in a carbon matrix. So carbon has a low atomic number, gold has a high atomic number. So we are going to see the phase contrast using the backscattered electrons. Then we have different kind of signals, like another important class of signal is EDX or characteristic X-rays. Viewers, you have used X-rays for different characterization techniques like X-ray diffraction or X-ray spectroscopy. Here in SEM, we are going to use energy dispersive X-rays in order to find out the chemical composition of the material. So there are two things to that. Number one, anyway we will discuss this again in detail. Number one is how to find which element is present in your system. Obviously, when we are having X-rays, we have characteristic X-rays. With the help of the position of a characteristic X-ray, we will be able to find out which element is that. So we will be able to identify the element. Now the second part is very important. That is how to find out the composition of the material. One is the identification of the element, second is the quantification of the element. For that purpose, we rely on the intensity of the peak. So once we deconvolute the peak, we will come to know about the composition of the material. Then we have cathodoluminescence. It can provide us information about the different information about the band gap of the material. So this concludes our signals. So today we are going to discuss three dominant class of signal. Number one, we are going to discuss secondary electron. Number two, we are going to discuss backscattered electron, and third, we are going to see the chemical composition using EDS, energy dispersive spectroscopy. Now the parts of SEM, as you can see, I have charted out different parts of SEM. The first to start with is the gun. We have different kinds of gun systems, like we have here in this case we have Schottky field emission system, and we can also have cold field emission, we can also have thermoionic field emission. So thermoionic is the most ancient system. Once they started fabricating the SEMs, they have thermoionic system. You have to heat the filament too much, but over the period of time you have used different material in order to find out different gun system. So field emission and Schottky emission have slightly different with each other. In one case of field emission, you are simply providing the potential in a very small area. In second case, you are providing a suppressor. So what is the role of suppressor? If you can see here, in field emission there is no suppressor, in Schottky emission there is a suppressor. So why we have applied a suppressor is only to make sure that whatever the beam comes out of the filament, it should have equivalent potential throughout. So many a time beam stability is the issue. We will see in the next slide. So here you can see current fluctuation in thermoionic or Schottky emission gun is less than 1%, whereas in field emission gun it is more than 10%. So beam should be stable. That is our concern. So to prove that point, we are using Schottky field emission, and how we are achieving it? By putting a suppressor. Okay, these are electromagnetic lenses. One of the key thing is in every system of microscope you have electromagnetic lenses. So you can see as you can see here, you have a outer jacket, right? And then you have soft iron pole pieces, then you have copper coils, right? And this is the typical construction of a electromagnetic lens. You have condenser lens. Now, what is the role of condenser lens? Please note, it is very important to note down the roles of different kind of lenses. Condenser lens is used to demagnify the image, commonly labeled as spot size or probe current in different SEMs. In objective lens, final lens in the column, commonly labeled as focus. Whenever we are changing the focus knob, in a second we will discuss the console of our SEM, that time we have a objective lens which is works into play. Okay, these are different kind of lenses like pinhole lens or immersion lens or snorkel lens. These are lens aberration. Viewers, one of the key things that we need to understand is at higher magnification, like we have lenses defects in our optical lenses as well, we can have defects in electromagnetic lens as well. So the beam which is coming out of the filament, it may not be completely circular. It may be extended in x or y direction. In order to make it again a circular beam, we have astigmator coils which will help us to make the again the beam circular. Okay, now we are into the final section of the parts. We have different kind of detector. As I have already told you, I have secondary electron detector, I have backscatter detector, and also I have the EDS detector, energy dispersive spectroscopy detector. There are only 2 to 3 slides more with me. Please bear with me, and we are going to discuss the operating parameters of SEM. One of the first parameter is accelerating voltage. Often people ask, my sample is insulator. The key answer is don't use high accelerating voltage because sample may charge or damage. So you can see I have two images. One is at 7200 magnification, other is at 25K. Same magnification at 5 kV and 25 kV. You can see surface features are more dominantly visible in 5 kV, right? Can you see? Right? In this image you can see surface features are far more visible than this image. This is at 5 kV, this is at 25 kV. Okay, now effect of probe current. If you increase the probe current, right? If you increase the probe current, what is going to happen? See, one is if you have large probe current, you can have a smooth image. But if the sample is a charging sample or an insulator, there will be a beam damage to your sample, right? Similarly, effect of working distance, as you can see, we can have objective or pole piece. Here you can see the working distance. If you increase the working distance, you can have large depth of field but poor resolution. So you have to keep these parameters in mind. So now with this presentation, I am going back to our console and we will discuss and let's see whether we have achieved the system vacuum or not. Okay, so viewers, vacuum has come, right? Earlier you must have saw there was a clock ticking. Now the vacuum has come. You can see the vacuum is well below the 5 into 10 to the power minus 5 millibar level. And now I am going to provide the EHT, electron high tension. Please understand the gun filament is always running. All we are providing or cutting off is the potential, additional potential. So you can see that there are different detectors in lens, SE2, then backscatter detector, and then TV. So right now the first detector I am going to employ is SE2 detector, or commonly known as Eberhardt-Thornley detector. So let us see whether we are able to focus few things. Now the first thing first, every detector has been calibrated in some certain given working distance range. For secondary electron detector or Eberhardt-Thornley detector, that range is 7 to 12 mm. Right? In a focused condition, your working distance should be 7 to 12 mm. For in-lens, you should be in between 3 to 5 mm. Similarly, for ASB detector or HD ASB detector or backscattered electron detector, you should be between 3 to 5 in the in-lens mode itself. Finally, if you are doing EDS, you should be in the range of 8.5 to 9 mm. Please note that it should be in a focused way. Whatever the working distance you are seeing here, unless the image is focused, is not correct. So I am going to take the stage up. First we will see the in lens image. So I am going very close to the pole piece. This is your pole piece. Now I am selecting in lens or through the lens detector. Same secondary electron signal, but the detector has been placed in a different position. Now viewers, I would like you to focus on the console. Here you can see that I have a gun. How much EST I have provided? I have provided 15 kV. It has been written here as well. Then beam is on. Finally, which aperture size I am using? I am using 30 micron aperture. What all aperture sizes we have? We have 30 micron aperture, 7.5 micron aperture, 10 micron, 20 micron, 60 and 120 micron aperture. These apertures has been used for different purposes. Then I have stage values. I can see where my stage is currently. Then vacuum level. What is the value of system vacuum? What is the value of gun vacuum? Which detector right now I am using? Right now I am using in lens detector. And then how quickly or slowly we are saving the image. Right now I am using at the scan speed of 7. Higher the scan speed, slower is the image acquisition. So if I have something like this, you can see the image is grainy. But if I try to save the image in line integration mode, image is captured very fast in 810 milliseconds. Whereas if I go to 7 scan speed, you can see the cycle time is now 20 seconds. But you will see the improvement in the image quality. Now I am going to see the backscattered electron image. So here you can see a backscattered electron image. Interestingly, on this side you are seeing the secondary electron image. Let me capture the image for you. So this side is your in lens image using secondary electrons. This side is your backscattered electron image exhibiting atomic number contrast using high definition angular selective backscattered detector. So we have already covered two of the dominant class of signals. Now we are going to see secondary electron image but using ET detector. So I have to increase the working distance. You can see now I will go somewhere around 8.5 at 2 lakh magnification in secondary electron mode or using ET detector. Now you have to observe that in lens at higher magnification I have a very good amount of image or very good amount of signal and brightness and contrast was very high. Image quality was very nice. However, in ET detector mode my image quality is not that great because I am at higher magnification and I need better resolution, which means I need a detector which can work at lower working distance, whereas this particular detector works at high working distance. So we have seen the operation of ET detector or SE2 detector, we have seen the operation of in lens detector, we have seen the operation of HDASB detector or BSE detector. Now we are going to do some EDS in order to find out the composition of different phases covered in the image. Okay, I'll make the image little better by changing the brightness and contrast. Now all I need is I want to measure the composition of this particle and this particle. You can see that gold thickness is not much. Therefore, the gold peak which is coming here, right, is very small and we are getting a very dominant carbon peak. So in white region I am getting two small gold peaks somewhere around 2.1 or 2.2 prior to that. So you have to be careful about the counts as well. You should have enough counts. Now I am doing the analysis in black region. So here you can see that there is no gold particle is popping up. Only carbon peak is there. That means the black region is purely carbon, whereas white region is showing some amount of gold. In a minute we will come to know how much is the gold composition in the white or bright region. So now let us see what all elements has been detected. The carbon in spectrum 2, and in spectrum 1 we have carbon and gold. So what is the composition? We can see that in spectrum 1, which is in the white region, we have 6% of gold, right? Whereas in spectrum 2 we have pure carbon 100%, right? So we have seen today how the different signals has been captured using different detectors in order to provide us the various kind of information. So this concludes our session on operation of SEM. Now we are going to discuss in a minute the different applications of SEM with different, we will see the different images which we have already captured and we have kept it ready for your kind view, and we are going to see how to take out the sample from the chamber. So now we have already covered the different kind of, three different kind of signal classes and three different detectors in order to find out the information using topographical, morphological and compositional modes. Now I am going to go to the gun console. I am cutting off the EHT. You will see the beam is going to be blank. EHT is coming down. Here also you will see EHT clock. So instead of green tick, it will become a clock. And finally a cross. Now you can see there is a cross, right? What we are going to do now is we have to go to camera mode, right? And then we have to go to vacuum. In order to take out our sample out of the specimen chamber, we have to break the vacuum. So initially we have vented it, right, and kept the sample inside. Now after pumping we have saw all the images and we have done the EDS, and finally we are going to vent it again in order to take out our sample. So now I am going to give the vent command. So I have clicked on vent. It has asked, are you sure you want to vent? Yes. And then you will see the stage will come down, and here also you will see the vacuum gauge has turned cross. So already we have gone through different applications and different material system. We gone through the images. We have observed how cross thin films, how your particle size and your different material systems like polymers, biological materials, metal systems can be used using SEM in order to observe the images and chemical composition. Now I am going to open the chamber. I am going to take out the material, and then finally before closing the video for today, I am going to pump it back, right? So now I am going to give pump command. So you can see vacuum is showing cross. The moment I will give pump command, you will see a dial gauge here, and finally once the vacuum is achieved, green tick will come here like this. So I am giving the pump command. So this concludes our hands-on operation session of SEM. I hope it will help you in your research. My regards. Thank you.